Hello and welcome to Pipeline Academy CAD Essentials lesson number 4. In the previous lesson we went over some more sketch entities and created a new assembly instead of just using a pre-existing assembly like we did in the first lesson, and we learned other tips and tricks about the software. In this lesson we'll continue to learn more features, and this time we will move on to another project, one that maybe is a little bit more similar to a project we might have at Pipeline Academy. Of course, this will be a much more simplified version, but it will give you a good idea of the workflow of how you might solve problems in the future. Okay, so let's talk about what the problem is. In lesson 4, our problem is that a customer has come to us. They have designed a fixture that should hold their device in place, but it doesn't. Now, we generally just call objects you hold in your hand that do a function a device. So you might have heard the term medical device in the past, but in this case, I guess it doesn't really matter what the function of this device is. It just needs to sit on this fixture while they're, I don't know, pushing buttons or pulling on it or some sort of testing or something. So first thing you want to start off with when you have a project like this is think about it, go back to your boss or your customer or whatever, and ask any questions that you may have. So in this case, we'd have a conversation and I'd ask if maybe I can press on the device, if it can handle that, or if it's too weak, it might crush if I have a solution that will press on it. So in this case, the customer says, sure, that's fine. We can push down on it to hold it in place. But maybe they also have expressed that it needs to be a cheap solution, that they don't want a highly customized solution that will cost a lot of money. So maybe now we're thinking more about off-the-shelf parts. And the term off-the-shelf parts just probably means what you think it means. It just means an object that you can go buy and use versus, some things that you'd have to have a machine shop make for you. So our favorite place for off-the-shelf parts to get quickly is McMaster, McMaster.com, just because they have a ton of stuff and they provide CAD models for a lot of it. So in this case, I'm thinking we'll get something from McMaster and maybe attach it to the customer's existing fixture. There's no reason to create a whole new assembly if we don't need to. Maybe we can just modify it and have it work for them. So here's what I'm thinking. It might be hard to tell. My mouse drawing skills are not very good, but basically here the red is the block, the blue is the device, and I'm thinking there's some sort of clamp that we can buy that we could just toggle this lever back here and that will push down or let go of the device. Pretty simple. And what we're going to be looking for is what is called a toggle clamp. It's very, we use a lot of Pipeline for solutions when you need something highly functional, relatively inexpensive, and you really don't care what it looks like. So I've gone ahead and looked at the website and drilled through and filtered out everything that I didn't like, and I came to the conclusion that this is the device that we want to use. Sorry, the toggle clamp that we want to use. The way these pages are set up is you get kind of a approximate picture on the top corner. It may not be anything like that. It just could be transmitting, high level information in that picture. And then a bunch of specs here, which usually you ignore all of the specs and just look for the things that matter to you. There might be some things in here like you don't care if it's ROHS compliant. So there's a lot of information in here, but you can just ignore the stuff that doesn't matter to you. At the bottom of the page, though, we see this drawing. That becomes a lot more helpful. These tend to be a lot closer to the object that you're going to get, although they can still be an approximation. Anything that has a dimension to it, you can pretty much assume what you're going to get is pretty close to that dimension. But if the handle shape might be rounded instead of kind of this rectangular shape or something. But the point is that this looks like it's going to work for me, and I think I want to integrate this into my assembly. Now, there are a lot of sites out there. If there's something that you need, you find the spec for it, like this drawing, and you might have to model it and then put that into your assembly. But with McMaster, they actually have this little drop down here that allows you to select from a series of files, and we'll select SolidWorks for this one and click Save, and that will just save to my default directory. Now, I've already done that, and I've placed a version of that assembly in today's lessons folder, so you should have access to it if you download the files for this lesson. I put everything in the toggle clamps part folder, or it's possible I rename this in the future, but you'll be able to figure it out. Now there's an assembly in here. You can see these are all SLD PRT, which is, PRT is part and ASM is assembly. So you want to click on the thing that's called the toggle clamp, and it's got the McMaster part number in there. I think I renamed that just so that it's a little bit more clear about what this is. Or you can use the open function in SolidWorks, but I'll just go ahead and double click on this. I'll rebuild it just to make sure I have the most up-to-date information. And here's the reason why I've provided this assembly for you. A lot of times when you download an assembly from McMaster, all of these parts are just going to be fixed in space. They'll be in the right spot for like the closed orientation or something, and then they'll be fixed. And that can be useful in a lot of situations, but sometimes you want to see how this assembly works. So I have gone through and added all the appropriate assembly mates so that you can grab the handle and swing it open like this and make sure that it works properly. Because a lot of times when you're making assemblies, you need to make sure that this opens all the way and that somebody can reach in and grab the device and pull it out. If it only opened up a little bit and then it was impossible to get in there and pull the device out, that wouldn't be a very good design. So sometimes if it matters, you'll have to go through and set this assembly up yourself. But for this lesson, I've already done this. So I've also opened up the fixture assembly in the CAD folder that you can download for this lesson. And it just looks like this. We have a dummy device in here that who knows what it does. Doesn't matter for this lesson, and that's sitting on the base that the customer has already designed. And we've proposed to the customer, what if we reuse your device, or what if we reuse your fixture and we just attach something to it? And they really like that idea. Sure, we could have designed something more complicated and made more money off of it, but I think generally you want to make your customer, make your boss happier by doing things more efficient, quicker, and cheaper if you are still doing it 100% correct. So let's go ahead and drop in the toggle clamp assembly, which you can do by going to the Insert Components command, selecting it from the list, and hovering over the graphics area and clicking anywhere you want. I've kind of approximately located it here. It looks like it's in a pretty good place, and then you rotate and realize it's way out of whack. So let's put in our first mate. I'll start by clicking on this. Actually, I want to show you a different way to select surfaces. We went over a few of them in the last lesson, but there are always more ways to do things in SolidWorks. So here's a new one. If we do a mate, if we open up the mate feature here, and I select the first surface that I want to mate, which is the top of the fixture, and now I want to mate that to the bottom of the toggle clamp. I know the bottom's down here somewhere. It's behind this wall, but it's certainly not this top one. If I press and release the Alt button once, it will hide the surface I'm hovering over and give me access to things that are behind it. So this is just another way to reach one of those hidden surfaces. So now I'll select the bottom of the clamp here, and you can see it move into location, and SolidWorks is guessing it's coincident, and that's exactly what I wanted. So I'll close out of this and drag this into the approximate location where I think it'll go. And things are starting to look good. You can see a little bit of interference here with the top of the device, but that's okay for a couple reasons. One, this is, if you look at the part on McMaster, this is actually a, let's see here. This is the tip material is stainless steel covered in rubber. So a little bit of interference here is fine because the rubber will flex out of the way. But we also can see here that this toggle clamp is adjustable. If we needed that rubber stopper material to go up and have less interference with the device, then the user will be able to advance the screw through these nuts and have a little less compression here, which is great that they can kind of dial in the amount of deflection that they want. So now we've got our first McMaster part dropped into an assembly, and we have to figure out how we're going to hold it down. Well, you might have looked at this and guessed that these 4 holes mean something, and those are basically screw holes, or so I'm going to guess. We could look at the spec here and see that it has, it actually comes with screws. Let's see, holding screws. It says 2 screws included. Those must be the screws that go through here. And then mounting holes, here we go. Number of mounting holes is 4 for a diameter of 3/16 of an inch. That's pretty useful information. Basically means we want to put a screw in there that is the outer diameter of that screw is smaller than 3/16 of an inch. And if we look at the drawing here, there's that dimension, this area here. Okay, I had to take a call, but we're back at it. So the diameter of this hole is 3/16 of an inch, so we just need to find a screw that is smaller than that. If it's the same size, it'd be pretty difficult to put a 3/16 inch item in the same size hole. You know, you might have to jam them together or something. So we'll find something a little bit smaller. And I have a very nerdy slide rule in front of me that my boss bought me and I use all the time. But you could just use the internet if you want to. So let's open up a new tab and search for screw diameter table. And we've got some options showing up here. I'll click on this. We're not seeing a lot of decimal points, but that's fine. We just need to see the nearest fraction to a number 10 screw is 3/16 of an inch. So remember, we want to go a little smaller than that. And the next standard size down is a number 8 screw. So let's go back to McMaster, find the right screw for us. That's a size 8. In some cases, these parts might actually tell you what screw you should put through the hole, or they might come with it. So it's just important to kind of look through here and see if that information is available. This wasn't that hard to find, so we went ahead and just looked it up. So if I go to the home page by clicking on the logo, the first option is screws and bolts. And then you could see a whole bunch of things to pick from, but for a fixture like this, looks don't matter and there are no extra considerations to make. We default on a socket head cap screw. So I'll select this option that's called a socket head screw. That is this cylindrical shape to the top of the screw. And once we're in here, there are more options that fit that. All sorts of things. And just like if some of the things we mentioned in the past, there are tons of options here. And unless you have a reason to pick them, generally just ignore them. Sometimes it's nice to know what's out there, so maybe someday you can go in here and just see what's around. But I'm going to look at the left here and start eliminating things that I don't want by specifying the things that I do want. So let's say in the material range here, I talked to the customer, they said this part's gonna be wet all the time, so let's select stainless steel. Now it shows us what stainless steel is available from the stuff that's left, and I am going to select 18/8 stainless steel. It's pretty standard. So is 3/16 stainless steel, but 3/16 is generally more expensive, we'll select 18.8. And you can see as I'm selecting these things, the options are changing off to the side here. Let's see. We've got a couple head options. You can get the normal size or one that's a little bit shorter. Again, we don't have any reason for a shorter screw head, so we'll just select the standard one. And we know that we want the 832 screw, or we know we want a number 8 screw. So I'll select 832 because I know that's the most commonly used version. If you were to look at, if you didn't know any better and you wanted to go, do I want 832 or 836? I'd imagine if you looked at the 836 screw that you wanted, with everything else the same as the 832, it'll be a little bit more expensive because it's less common. So sometimes you'll find a little direction on McMaster as you start drilling down through these myriad of options, because eventually you'll get to the point where you can see one part is cheaper than the other one, and you can sort of guess that that's because so many people order it that they have that's like their most common, less specialized version. So I've drilled through a lot of stuff here on the side. Length is a good one to consider. So if we go back to the CAD assembly, that's not the CAD assembly. Here it is. We've got this in here. I can select this top surface and this bottom surface to see that this plate is 0.078 inches thick. So we need the screw to go through that plate and into the material, and generally you want it to go in 2 diameters of the screw. So we can actually go back to that table and we can see the diameter of a number 8 screw is 0.16. So we want it to go into the material twice that amount, which is 0.32, and then add the thickness of this flange, which is 0.08. So let's see what options are available. And generally they won't have an option here that's not available. So a ½ inch is fine, close enough. And we still have a bunch of options here. All these look pretty specialized. I'm just going to pick the normal one on the top left, which is usually the case. And then now you can start seeing item numbers pop up. When you drill down enough and you get rid of all of the special cases, it'll eventually start showing you this list of parts. And I can see here that stainless steel, in fact 18.8 stainless steel, has 3 different finishes available, also reflected down here. And if you look at the pricing of these various things, you can see for 100 pack of these screws it's $6.88, and then these are all very expensive, right? $9 for 5 of these, $6, which is less than $6.88, but for half as many. So this helps you make this decision a little bit more. So I can tell that the most used thing, the most like generic thing, is this one, kind of based on cost. So you don't need to worry about figuring out these other things yet. So if you select this part number, it'll take you to the product page that looks similar to the toggle clamp. Or you can continue to drill down through the options by selecting things on the left side. I'm just going to select here and then do product detail. Again, we've got like a table here that shows various information. Unless you care about something specific, then you can just kind of ignore this information and just kind of cherry pick the stuff that does matter to you. So this is looking pretty good. I need to download this and put it into my assembly. So let me, I had previously selected SolidWorks in another part, so it's just going to stay selected here. If you had messed around and maybe grabbed a PDF before, it might say PDF here. So just always make sure you're downloading the correct file type, hit save, and then when it's downloaded, you can drag it into your folder where you keep your files. You can see the file that was downloaded has this really long name, and it's not particularly helpful. So here at Pipeline, we like to rename it just with some high-level information. You could be here all day making a really long part number and name for this, but I am just going to rename it with some helpful information. So I'm just going to delete this and name it an acronym for socket head cap screw. And it's an 832 screw, and it's 0.5 inches long, and it's from McMaster. The place you work for or a preference of yours might be different than this, but this is just this is much more useful than what they name their files. So I'm going to take this and drop it into my project folder, which I believe is still open in the background. It's not. Let's see. Let's go. Here we are. And I'll just paste it here. It's important to paste it here because if you opened it up while it was still in your download folder and put it into your CAD assembly, it would work just fine. But it's possible in the future you decide to clean up your download folder and you delete everything from there, and you don't realize that the assembly somewhere else on your hard drive is looking at that file. The next time you open up the assembly, it'll look in your download folder and it won't find the part, so the assembly won't be able to load that information. It'll give you a big error and nothing will, and that part won't load in the assembly. You could avoid these types of headaches by just always keeping all of the relevant parts to an assembly in the same directory until you're given a reason otherwise. Lots of workplaces have various things like what they call PDMs and other types of file management tracking systems that might affect your workflow. But you sitting at home working on your computer, it might be a good idea just to keep all of your projects isolated into their own folders so that you don't ever accidentally move or delete a file that would be used in an assembly that you can't remember it was being used in. So in this case, I've moved it into this project folder, and we can open it up from here and drop it into the assembly and be relatively certain that in the future we're not going to accidentally move this part. So I'll hit enter to open it up, and you can see that McMaster has provided us with this beautiful assembly, or I keep calling it an assembly, this beautiful part that has all the features that might be relevant. So we'll go back over to the assembly, we'll insert this screw, and we're ready to go. Now all we need to do is put a hole in the top of the part to receive the screw, so the screw can hold the toggle clamp down, and that's pretty simple. If I go to the part, I want to add 4 screw holes because the part spec said that's how you hold it down. And the way we like to add screws to a part, and the way you should do it, is use the hole wizard command. For the most part, in almost all situations, you're going to use the hole wizard to create holes in parts. And of course, you're always going to find reasons to kind of break from the norm, but in most cases, you're going to use the hole wizard to do holes. And it's a great tool to use because SolidWorks knows all the kind of standardized hole sizes for the things you're trying to do. So if I'm trying to put a hole in a plate so I can put a screw through it, SolidWorks knows what size that should be if I know what size the screw is, and a bunch of other fine details like that. And it also helps when you make a drawing. If you've used the hole wizard, it's easier to kind of specify what are the important details about that hole. So there are a ton of options here, and it might be overwhelming what you see, but we will get to them all eventually. Right now, let's just focus on this straight tap. anytime you see a hole that has these dotted lines around it, and it might be hard to see in the stream here, but if you open up SolidWorks and look in the same area, you'll see a dotted line all the way around this hole, and that kind of is the universal sign for this is where screw threads are. The other features don't have that, which means these are just normal holes that don't have threads in them. And that makes it really hard to put a screw into the hole. So let's use the one that has threads. It's called straight tap. The next option down is, do you want inches, metric, or a bunch of other stuff? But we're going to stick with inches because we know the drawing told us the hole through the clamp is 3/16 of an inch in diameter. So we know we're in inches. It didn't say it was 8 millimeters or anything like that. And then we can select the type of tapped hole. I'm going to leave it at default, but you can change it if you find a reason to do so. And then I'll select the screw size that we selected from McMaster, which was an 832. So I can just scroll here to 832. And then I can specify how deep I want the end of the hole to be. The thread itself, we could say is 2 diameters. And then the hole itself, we can make blind longer than the screw diameter. We'll explain that in a moment. Then we have a couple options down here that you could just leave as default. You don't really change these that often. You just kind of figure out what you like, and then these always just kind of stay here. So now that we've sort of defined what each hole looks like, let's tell SolidWorks where to put the holes. And that's this other tab up here called Positions. First thing it'll do is ask you which face to put the hole. So I'm going to click on this top surface here, and then it immediately starts showing the preview of where the hole is going to be. It might be difficult to see there, but there's sort of like an imaginary hole position. So it's kind of difficult to see what we're looking at here. So I will look normal to the surface by hitting Control 8. You could also use the space bar to do the same thing. And I'll draw my first hole up here. It looks like a pretty good idea on this assembly. Just kind of have the clamp centered from left to right, and we might come up with a reason in the future to make it offset or something, but it just seems intuitive to keep it in the middle. So we're going to have something that kind of looks like this for the clamp, and you can kind of see the little hole previews there, which is looking good, but I want to be a little bit smarter about how I make these holes. So I will delete these 3, and I'll start dimensioning this. Again, Control 8 makes me look normal to the surface. I'm going to dimension things from the origin. I'll just put these sketch lines here. Doing it in a weird way, but it works. Rather than dimension things to this feature, I'm going to dimension it to the origin. That way if somebody changes the shape of this feature, this doesn't move around unintentionally. And you can look at the part spec for that clamp, or you can go measure it in the here we go. Here it's telling me the distance between the holes. So if I put those dimensions in, I know it'll match up. So we got 5/8 from one side to the other, and then 17/32 from front to back. So let's do dimension from here to here. I think we talked about this before. This shows the dimension from the center line to the point, but if I come to the other side of the center line, it imagines what the distance would be between like a mirrored component. And from that side to that side, it was 5/8. I could type in the decimal equivalent, or I could just say 5 divided by 8. And then we could do another one of these and give that a height 17/32. And then I'm going to put a dimension from here to here. If we look at this, looks like we could probably put the not easy to tell from these dimensions here, so I'll estimate that this has to be about an inch from the center line of the device. And then you can still see this is blue, stuff can still move around. So I think I want these to be vertical. There's no reason to have my clamp rotating in place. And I can see both of these points have gone black instead of blue, which would mean they're underdefined. And then now I need to mirror these across, so we have a total of 4 holes. So entities to mirror, this point, and mirror it about this center line. There you go. So now we know if we drill these holes, we'll be able to align the toggle clamp with it. I'll go ahead and hit accept. You can see these little lines around the hole are an indication that the hole is tapped. SolidWorks won't go through and show the little helical shape that a tapped hole would have that a screw would engage with, because that takes processing power, and it's not really necessary to show those details. If I tell the machine shop, drill a hole here at this point and make sure that it has an 832 tap, then they'll be able to do that, and they don't need to see the helical shape. So we're all set here. There are some other settings to make this look more apparent, which we can talk about in a later lesson, but this is what it looks like by default apparently. Looks different on my computer because I must have changed it a long time ago. So now I've moved over to the assembly and we can see that the holes are showing, and we could start locking down this toggle clamp. The easy way to go is just to select one of the holes in the toggle clamp, one of the holes in the plate. By holding control when I selected them, they stay selected, and then I can hit concentric. And then now this seems to rotate, so maybe we'll make another hole concentric. And now there's a problem here. So one thing you might find is that stuff might look really close to being the same dimension, but if it's not exactly the same dimension, SolidWorks won't like it. So if we just look at the part, I can measure from one hole to the other by selecting both of the holes and then hitting the M key for measure. And that pops up just like this. You see this little window, shows you a whole bunch of information, and it draws stuff into the world here. It's showing that there's 16 millimeters from one side to the other. So the dimension that I put for the holes was based off of the McMaster drawing, but it appears as though the model they use is slightly different, which is a great example of how things from McMaster might be a little different. So if we look at the McMaster page, it says 5/8 of an inch from there to there, and we had calculated that 5/8 is 0.625 inches, and if you look at this, this is reading 0.623, which is 0.02 of an inch off. It's probably not enough to make a difference in this assembly because it's not like a high precision part. It would give me a little pause though that this CAD model doesn't match what the drawing says, but we're going to soldier ahead here and just keep this going. So since I was able to just select this surface and hold Control and select the other one and hit M and measure this distance as 16 millimeters, then I can go ahead and update the hole wizard to reflect this new dimension. A couple ways you can do that. Again, you can click the down arrow and find the sketch that defines these holes, or you can double click on one of the holes and see the dimensions that are shown and just kind of edit the dimension without going into the sketch. Or you can go into the edit feature and select the positions tab, whichever one is your favorite. So here, instead of 0.625, we want to put 18 millimeters. 18 millimeters? 16 millimeters? And I'll switch over to the assembly. Now, if I take this hole and mate it with this one, the mate is successful. There were no errors that popped up. And if I try to drag this part, it doesn't move. You can actually see here the minus sign has disappeared from in front of the toggle clamp, which means it's fully mated and it can't go anywhere. That's great. Now let's mate this screw. I will grab a cylindrical face on the screw, and what I like to do is mate it with the hole itself. I could mate it with this part, and that would be mostly fine, but it's nice to mate any of these to the part that they're going into specifically for a variety of reasons. I'll do this first to show how to do it. There we go. And then we need to attach this to the bottom, so I'll select this surface, right click, and select the one behind. There we go. Now the reason why I like to mate this to the hole in the actual body of the fixture instead of mate it to the hole in the clamp is because it would be easier for me to see if something goes wrong here. I guess it's a small issue, but it's possible that somebody changes the dimensions somewhere and the hole underneath the part moves to a different place. But because it's underneath this plate, I might not be able to see this hole move to a completely nonsensical position. If the screw is mated to that hole and this screw travels all the way over here and it's like sticking halfway out of this plate, it's much easier for me to see that that hole has moved to the wrong place. It doesn't happen a lot, but especially when you're working with the assemblies and parts that a lot of people use, it's like a nice little thing, like why not just do it this way? And that way you can avoid any potential issues in the future. So again, as with the problems with any screws, these are, this rotates. I don't know if we discussed it before, but while you're doing the concentric mate, which I guess I'll kind of reiterate how we get to these mates. If you want to see a mate that one part is using in the assembly, you can click the down arrow and there's a folder called mates in, and then this is called fixture assembly. That's the assembly we're in. If I expand this, I can see the mates we've made. So this concentric mate has this option to lock rotation that you can use so that when you add a concentric mate, it can't rotate anymore in the future. So in previous lesson, I advocated for making a plane in this part parallel with a plane in the part you're mating it to, but you can go ahead and just lock it down so it doesn't rotate. Actually, I think we did talk about it because I explained this icon shows that it's locked in place. It saves a little bit of time, I guess, but it also could make it look weird if you're particular about, you know, every screw being slightly rotated in a different way. I don't know. Doesn't matter that much. So now we've added our screw. It's starting to look pretty good. Maybe I want to make sure that the screw's not interfering with this hole. There's a variety of things we can do, but the easiest thing to do is make this part invisible. Better yet, make it transparent. So if I have nothing selected and I select this surface, this little pop-up comes here. and I can keep hovering over these things until I find the change transparency option. If I select that, it makes this part transparent, and then I can kind of look in here and make sure that that screw isn't obviously interfering with the plate. And it seems like it isn't. It's perfectly undersized. I can undo so that that part is no longer invisible, or if it is, I don't know why I keep calling it invisible, I mean transparent. If it is transparent, I can click on it and then make it untransparent again, or opaque, I guess. The difficulty with that is if it's transparent and there's a part behind it, you'll select the part behind it. I mean, that's sort of part of the reason why you might make something transparent, is to select stuff behind it. So that can be a problem when you're trying to make something opaque again. The easy solution to that is just rotate the model so when you select the part, there's nothing behind it, and then you can do that. Or if you know the name of it, what you can do is expand this by hitting this arrow on the feature tree. You see a whole bunch of confusing stuff down here, but anything that's transparent will have a little icon here, and if you click that, you'll remove the transparency from it. There we go. So now we've confirmed there's no interference, which is great, but we only have one screw. So we can do like we did with the coasters and create a copy and then mate it to all of the different holes, or we could use a pattern. A really nice thing about using the hole wizard is now I can tell the assembly to copy this screw for every hole we've drilled. So as long as all these holes were done under the same pattern, which they were done under the same feature, that hole wizard, we did the hole wizard once and I made 4 holes, I can use that information and just tell SolidWorks to put as many holes in there as there are, as many screws in there as there are holes. So here's what we're going to do. In the assembly tab, there's something called linear component pattern, which is helpful for a lot of things, but we're going to hit the down arrow and go to the pattern driven component pattern. I don't know if that's an intuitive name, but it works really well. So we'll select this pattern driven component pattern. We'll tell SolidWorks what to copy, and then we'll tell them what to look at when they're creating that copy. So I'll find one of these holes in the hole pattern. Oops, I need to highlight this first. Select one of the holes in the hole pattern, and then SolidWorks will fill it in like this. It's possible that they don't quite align correctly, so you might have to select seed position here, and then it'll show you each position that it might start from, and then you can select it. So maybe when you started doing this feature, you start it up and you see this. You're like, this doesn't make any sense. The 4 holes are over here, and then these are over here. That doesn't make any sense at all. So then you can select seed position, find one of those options until you find the one that makes the most sense. So there you go. Now you can see that they're all in the right spot. So if I accept this, you can see that all 4 of those screws are patterned across it and kind of all hidden in this feature called the driven hole pattern 1. And there they are, these 3 screws. So the original screw is still up here, and then this feature copies it over 3 times. An interesting thing about this feature, about making this a pattern-driven pattern, I hate that they call it that, is if I open this part up and I modify my hole wizard by, let's say I wanted another clamp in here. I'm just going to approximate these and accept it. Now I've got these 2 sets here. And go back over to the assembly. That pattern is going to look at the hole wizard again and go, oh hey look, there are 4 new holes, let me put 4 new screws in there. So that's really handy for a variety of features where if you set it up this way, the pattern will update automatically. In this case I don't want those, so I'll go back into the sketch I'll just draw a box around them and hit the delete key, close out of the drawing, and after a rebuild, those new screws have disappeared. I will save my work. You might see this little green bar across one of these saved items, and that just means that whoever worked on it before had used it in an older version of SolidWorks, and there's not a lot of great backwards compatibility in SolidWorks. So just make sure you're not ruining anybody's day by saving an old SolidWorks file as a new SolidWorks part, because you're pretty much guaranteeing that the person who made that part can no longer use it unless they install a newer version of SolidWorks. There we go. Now it's saved and we can have a look here. You can see the little stopper is a little bit off center, but I think that's fine. You can see there's some adjustability here. The entire screw can slide backwards over the center line. If we wanted to, we could update this assembly to actually bring back that screw, but we don't need to right now. All right, I was interrupted by another call, but let's go ahead and finish this lesson so we can get onto the next one. One thing that we might want to do now that we have the assembly fully completed is to check that it might actually operate the way we want it to. You saw earlier that I had the toggle clamp set up so that it can open and close, but if I grab this handle and try to open and close it, it doesn't work. And that's because by default SolidWorks does not allow components inside this assembly to move. We call it a sub-assembly because it is an assembly, but it's not the assembly we're working on right now, right? This sub-assembly is included in the entire assembly that we're using here. So by default, SolidWorks won't let you move parts around that are inside of that sub-assembly. If I opened this and grab the handle, it still works. But if I switch back, it's not going to move unless I do something about it. So it's a really easy thing to change, and you might do this at some times to do your check, but often, usually, you know, the majority of the time, your sub-assemblies don't move. In this case, they do though. So I will come over here to the sub-assembly in the feature tree and right-click on it. And if you look at this icon where you can see, it's sort of a version of the assembly icon. If you remember, that yellow piece with the blue piece stuck to it is the assembly icon. Here you can see the blue piece is kind of drifting away, and that is to indicate that if I click on this, or actually I'll hover over it first so you can see, it says make sub-assembly flexible. So that might be an unintuitive word, flexible, because we're not really flexing anything, but this is what we use. If you click on that, it will allow all of the mates that define that sub-assembly to become active. So the things that are in it that allow this component to move can now operate instead of it just being frozen in space. Now, this stuff takes up more processing power on your computer and more memory and stuff like that. So usually you won't have this activated all the time. You know, you might come in here and check and everything and then lock it back up. So the reason why I'm doing this is I want to make sure that this device can come out of the fixture. Otherwise, there could be a problem. So if I grab this and pull it to its open position, it looks pretty good. You can grab that out of there. You know, this is a simplified version of what the actual fixture looked like. So obviously we would have made some considerations as far as clearance for fingers to get around this part, and you know, just basically ease of access improvements and things like that that you can do to this. And I think actually the final fixture from the real version of this task. We replaced this rubber plunger with a custom shape to distribute the load across the device instead of just leaving the rubber stopper. But there are some projects where we've just had a rubber stopper press on a thing that can withstand sort of that focused force. So those are some of the considerations you might make in a project like this. Now that I've confirmed that this works, I don't necessarily care that it stays flexible. So I would probably go back here and make it rigid again just by reselecting the flexible feature. And now it won't move anymore. You will note that even though it's a flexible part, all of the parts within it, none of them have the minus sign next to it like they're underdefined, and that's because this assembly is not underdefined. The definition of like defining the mates isn't necessarily that nothing can move, it's more that every movement is planned. Usually that means no movement at all, but if I expand the mates in this assembly and you can do the same on your computer, I've put some advanced mates in here, including this thing that's called a limit angle that allows this to open to a certain point and stop and close to a certain point and stop. You might have noticed in this presentation though that there's some limitations. SolidWorks will kind of allow you to stretch past and pop over any strict limit, and then sort of the part appears on the other side of the limit and things start looking weird. And that's just a limitation of SolidWorks kind of allowing you to kind of pop over it, I guess. It's unfortunate, but it definitely still gets the job done here. But the important thing is that this is fully defined. So if you want to have a look at this assembly after this lesson and have some more practice with it, what I would recommend is for you to go into the part and create a new set of 4 holes, and then mate a new set of this toggle clamp and screws to that new set of holes. You can experiment with the various ways of how you might pattern these 4 holes into another position, or you can just draw 4 new holes, and you can experiment with ways to pattern these components based on what we've seen here. Just remember, it's the more you can have these things update automatically, the better.
If you found this content helpful, consider enrolling in our signature program at mypipelineacademy.com. Whether you're an individual interested in beginning a new career as a mechanical designer or a company interested in training your new engineering hires, our signature program helps students develop the practical skills they need to be productive mechanical design engineers. Seating is limited. We hope to see you there soon.